So, as I've said previously, everything we've gone through in this class up to now, particle in a box, the harmonic oscillator, the rigid rotator, the hydrogen atom, these are all problems that we can solve exactly. The solutions are not trivial. They get pretty complicated, as we saw with the hydrogen atom, but they are problems that there are known exact solutions. We can find the exact wave functions that have specific eigenvalues, that have energies that we know precisely. But for anything beyond the hydrogen atom, which this is it doesn't feel like it, but this is a chemistry class. So it's a physical chemistry. We care about a lot more than hydrogen. So we'd like to be able to look at things like helium, add an extra electron, or, methane, right? We'd like to look at molecules and understand their quantum mechanical behavior. And we can't solve these problems exactly with the approaches that we have. There is no known mathematical way to write down all the electrons in nuclei in a methane molecule and get an exact solution for the Schrodinger equation. And so we rely on ways of finding approximations that let us get very, very close to the right answer, and often essentially the correct answer, to the best of our ability, especially with the advent of computers. Computers allow us to do a lot of these approximation methods very quickly, and we can, get very close to real answers. I should say real to the what the real values are that go with our system. And so in this chapter, we'll be looking at the two major approximation methods, sort of from a bird's eye view, and getting a little bit specific. So the first approximation method that's used, it's what's known as the variational method. And that's what we'll cover in the first half of the chapter. And the second major approximation method is what's known as perturbation theory. So these are both ways of taking what we know about the system and trying to find wave functions and eigenvalues that are as close as we can get to what should be the correct answers. In the variational method, we use something called a trial wave function. We guess what the wave function should look like. Knowing what we know about quantum mechanics and about the system, we pick some function that we think will be close, and then have a way to improve it, right? So we have a way of varying it. That's why it's called the variational method. We have a way of varying this wave function to make the answer better. In perturbation theory, we start from a known system, something that we know the solution to. So something like the hydrogen atom or rigid rotator or the harmonic oscillator. Start with known solutions, and we treat what we can't accurately model as a change, what we call a perturbation, that we add to that known solution. And then perturbation theory gives us a way of finding wave functions and energies and things like that from adding this perturbation on. So in the next video, we'll start looking at the variational method.